So I'm going to be talking about this project Terminus that's been, we actually started in 2016 at Microsoft and has been chugging away and actually is kind of the underlying, kind of vision of what we've been doing in some of our SmartNIC work. This is joint work with MSR Asia folks, Ran, Lei, Peng, Yong, Chiang, as well as people from my team, Ram and Mark and Steve, and Arun is our Azure core collaborator. And we work a lot with other people on his team as well. All right. So going to, this is just a brief introduction of what public cloud is. It's actually a very, very large and rapidly growing business. So as you all know, well, in terms of the size of the business right now, according to certain numbers, which I don't know how true this is, but according to the numbers that I was able to find on the web, it's 490 billion in 2022, expected to be 591 billion in 2023. This is actually comparable to the total semiconductor market. So if you look at all of the semiconductors sold, these are, your processors, your cell phone, all of the silicon that we sell, it's about 571 billion. And we, obviously cloud is growing. So we're at some point, it's potentially, the people are talking about a $2 trillion TAM. Total addressable market. So it's a very, very big business. And really what we're selling is we're actually renting things. What we're renting is, these are virtual machines that appear to be bespoke computing systems created by partitioning a server. So what do I mean by that? I can go and rent a 8-core, 16 gigabyte VM with some SSD and so on. I can access it over the internet. I can log into it. I can access it. I can run my services like my web server or my customer relationships or SQL or whatever. I can run on those particular VMs. The nice thing about these is they're right size for the customer workload, which means the tenant can say, look, I need this many cores, I need this much DRAM, I need this much disk. And you can actually ask for it, and it basically gets created in about a minute. So you can imagine this is super convenient if you see, a large amount of activity on your website, some YouTube influencer just, said, mentioned your particular product. All of a sudden you're ramping up in terms of looks and sales. You would like to be able to dynamically increase the number of VMs you have to be able to service that unexpected load. So this is really advantageous. And obviously during Black Friday, we see a huge spike in business and so on, because people don't want to own all these machines all the time. They want to be able to rent them as they need them. So it's interesting about this is in terms of how much they cost, right? So I went and looked at the local Azure VMs, and they're about, it depends on a variety, many things, but they're about $60 a core plus 8 gigabytes per month, right, for latest generation cores. So that means for a 100-core server system, that's $6,000 a month, or $360,000 for 5 years, right? This is super expensive. When I actually showed this to a senior technical fellow at Intel, he's like, "Wow, we charge a lot less than that when we sell you these processors." And I'm like, "Yes, but there's a lot that goes into running a cloud, right? We have to pay for the data center itself, the physical building, the air conditioning, the power delivery. We have to pay for the people managing and so on. And really, you can't look at it as, comparing it to the cost of purchasing the thing, because this is exactly what we do when we rent hotel rooms, we rent cars, we rent wedding venues and so on. It's not economical for us to own all these things all the time. We can't own a place in Hawaii where we go on vacation 1 week out of the year. It's much better for us to just rent it, even though it's going to be more expensive for the days that we're there than if we owned it for the entire year, looking at it on per day cost. Right. So the other thing is this cloud service provider is generally more efficient at providing VMs than the customer. If you go and look at how much a customer, if you wanted to go and run your own on-prem server, it turns out it's very costly. I actually met a guy who was running Sony's cloud presence in the Bay Area, and I asked him how big it was. And this was a few years ago, but he said it was one rack, right? And so it was one person managing a whole rack. It turns out that that's probably going to be more expensive than, just renting it from us, as they need it. So, okay. So what's my ideal cloud, right? So if we go and step back, this started as a research project. What would we really want for as an ideal cloud? And so these are 3 things that I think are critically important. One is bare metal, the capability to be indistinguishable from a custom-built dedicated on-prem machine. And so what this means is a tenant should be able to get access to any control register that they want, be able to manipulate anything they want within the system. It shouldn't be able to tell that the tenant shouldn't be able to tell that there's someone else running on the system. That's they shouldn't be able to tell and shouldn't be able to observe anyone else running also. So that we should be able to eliminate any side channel attacks. The tenant should have absolutely predictable performance. Any jitter that's introduced is jitter that the tenant themselves are creating, not from somewhere else. It turns out that in real systems and real cloud systems, you sometimes do see jitter caused by other tenants or by the cloud service provider itself. You also want to have confidential compute capabilities where the tenant doesn't have to trust the cloud service provider, don't have to trust Microsoft developers or Amazon developers, whoever who is running that cloud. We want to be able to be very, very secure. And so really this bare metal is it should be, is a requirement that I would like for my ideal cloud. I also want to be able to generate an arbitrary configuration of components, right? So one core, 1,000 GPUs, half of an FPGA, and 1.5 SSD. So can a tenant get exactly what they're looking for, and which actually may consist of components that are not practical for us to put into a single server. We cannot put 1,000 GPUs into a single server. And the other thing is we want to maximize our offload, meaning that we want to move all of this capability, all of this functionality that is needed to support this ideal cloud. We want to move it from running on those cores, which are opportunity cost $60 a core per month. We want to move all that work off somewhere else, right? So fundamentally, that's what I'm going to call offload in this talk. All right, so yeah, goal here is, we're going to be carving out machines from the data center, but as far as the tenant's concerned, it sees a dedicated set of resources that no one else is consuming any of them. Right? Okay, so this is supported by Terminus, which is a North Star logical tenant CSP interface vision. Think of Terminus as a next generation kind of hypervisor, which is implemented both software and hardware and distributed across a data center, or potentially even beyond a data center. Okay. There are many ways to implement Terminus. We're going to discuss a few, and this is really the motivation for Terminus. A lot of people, I got a lot of pushback on the name Terminus when it first came out, because someone was telling me like there's some horror movie, Dawn of the Living Dead or something, where Terminus is where zombies lure the humans to go and so that they can be eaten or something. I don't know what Terminus and also people are like, oh, is this Isaac Asimov's Terminus? From his Foundation series. Really where the name came from is we first started looking at kind of a centralized terminus where you can imagine having long haul Ethernet then gets spliced, is a place to switch into your local subways, your local buses, your local taxis, and so on. It's basically an interchange where you basically have to go and you're moving data, but you're changing the direction you're moving. You're figuring out the next level of virtualization so you can get to your final destination. All right. So what does Terminus require, right? So what is this, what do we need to make Terminus work? And really the four key components of Terminus are what we call VISC. So the first is virtualization. So we need the ability to virtualize our network. For example, tenants need to be able to send and receive messages using their own IP address. So if you think about being able to go and expand an on-prem offering, where I'm running in my own data center, I'm like during Black Friday, I need to expand into Azure. What I probably want to do is I want to be able to use my own IP addresses. And if I use my own IP addresses, now I can go and just it really doesn't look any different. I can just go and start sending messages to the cloud, to Azure, when I need to spill over and then things come back. So this is a very simple example. Sending message to Chris, which Chris depends on the tenant, which means that, fundamentally we're doing virtualization of all the IP, of all these messages, these Ethernet messages. We also do, virtualization of storage. We access virtual disks. We need to translate to where the data actually is. It might be replicated, it might be remote, and so on. So there's a bunch of things that need to happen when we're virtualizing network and storage. And these are just two of the virtualizations, but they're the main ones, right? They're the main IO virtualizations that we will do in this kind of capability. We also need interconnect. So interconnect I use as effectively, the ability to move data around, right? So you need this for tenant communication. You need access to remote components. This includes things like Ethernet or PCI or the combination of both, and DMA engines and so on, right? So you need the ability to move things around. You need security, right? So you need to isolate to protect tenants and CSP secrets. You need to figure out how to get confidential compute in and appropriate access controls. And you need quality of service, right? So each VM is guaranteed its own resources, whether it's cores, DRAM, bandwidth, and so on. Obviously, you may have a work conserving scheduler, which allows you to consume resources that others are not using. You may not want to enable that either for yourself or for others to use your resources if you want things to be very controlled. You don't want to have any side channel attacks. You may want to say, look, I want a time division multiplexed, slice of the interconnect or whatever, which allows you to prevent anyone from seeing what you're doing. But fundamentally, this is something that we want to be able to guarantee, at a variety of different levels, what a tenant might be able to expect. We want to eliminate jitter with quality service and ensure isolation for performance and security. And if anyone has any questions, just feel free to call them out. Again, I can't see anyone raising their hand, but yeah, just go ahead and ask. All right. So if we look at early cloud, how do we virtualize in the past, right? Well, the way we do normal virtualization is, the processor is the center, right? Everything is attached to it. And what we did is we ran all of our virtualization capability in software, right? So if in fact, there was something that we needed to go and virtualize and not allow this particular tenant to run, we would do trap and emulate. And effectively though, everything was being run in software. One thing to point out here is that any core running at the right privilege level can change any processor hardware configuration, right? So this fundamentally doesn't support bare metal. We can't have a bare metal offering. That's pretty obvious in this particular, early stage where everything is purely done in software. So an example of this, of course, is VMware hypervisor. And what the hypervisor is really doing is moderating access to all of the shared resources, right? So cores, DRAM, disk, network storage, accelerators, everything is being moderated through that hypervisor. So effectively, tenants make requests, the hypervisor essentially will go and interpret those requests. Now, when you do that, you can certainly do this, and we've done this for many, many years. The problem with this is it consumes a significant number of cores, right? How many cores is depends on how much load it is, but it's significant. And so what this does is, number one is it's an opportunity cost. Those cores could be rented out at $60 a core per month. We can't, because we're saving some of them to run this virtualization infrastructure. If we don't, or even if we do, it will introduce jitter, right? So when one tenant is accessing the network, the cores are being used to go and virtualize those network accesses. Now all of a sudden that core core usage and the DRAM usage associated with that core winds up potentially introducing jitter to other tenants. Tenants hate jitter. In fact, the highest paying, the tenants who are willing to spend the most money in public cloud would actually prefer to minimize jitter, because even if you have a lower average performance but you have high jitter, you need to go and bake that high jitter into whatever the service level agreement is to your customers, to those tenant customers. So fundamentally, we really want to keep jitter under control. Jitter obviously can be caused by the tenant themselves, but you want to minimize the jitter created by anyone else. And so this consuming of large number of cores has that issue. The other thing that comes up is limited security and quality of service. That basically you're doing all of this in software. There's a very limited amount that you could do, and there are side channel attacks created because the cores can actually interfere with each other, right? So I'm going to switch to slides that Mark Russinovich presented back in October of last year, talking about our system, which is we did this offload. So if you look at the traditional infrastructure, network and storage, I/O processed in the host OS, right? So fundamentally, which is the hypervisor. What we're really doing now is we're going and moving that. So rather than going and doing that, on cores and on the processor itself, we actually go and move things off to an accelerated offload. We're running agents which control all this, and the storage and networking I/O capabilities are being offloaded to this additional piece of hardware. All right. So you're really moving center of control from processors, which used to be doing all this, actually to the offload engine, to this accelerated offload, right? The server, the center of the server is moving from one point to the other. Okay, and so how can we do this? Well, the way we do this actually is on an FPGA along with an ARM SoC, which will run software agents. So we run software agents here, and basically the storage data path and the network data path and even our NIC are being all implemented inside the FPGA. And so basically storage and networking are offloaded to virtual functions on the FPGA. So what happens is the VMs actually see those virtual functions. They can talk directly to the hardware. They don't need to go through that hypervisor anymore. They don't need to consume the cores. They just talk directly to virtual functions that are implemented in the FPGA to access the networking and storage paths, right? Yeah, so, and then these get connected to the top of rack switch. So if we go, this is actually a board that picture board that Mark presented. There's this has an FPGA in the ARM sock, and obviously this has been in production for some time now, and so this is just a prototyping board. But the ones that are deployed look much better than this and don't have fans hanging off of the FPGA and so on. Okay. So now moving on to, what's the next generation? So next generation is going to be a discrete terminus. So today, rather than having everything being attached to that processor, which currently is the center of the universe, imagine if we now go and have a terminus node. Think about that giant railroad, cross to local rail and subway and so on station. We've got our long haul, which is going to be our network to Ethernet. And then we've got basically, our ability to communicate to individual components inside the server itself. So instead of going and connecting everything to the CPU, let's connect everything to Terminus. So Terminus is going to require lots of PCI lanes, but this is something where we know it's possible. Think of this as a very smart PCIe switch with Ethernet capabilities. So in this particular case, we're moving the hypervisor from the CPU into Terminus. We're attaching peripherals like the FPGAs, the SSDs, GPUs, and even NIC. It all gets kind of folded into this Terminus node. And once you look at it this way, you see that the processor that has this PCIe switch in it, we don't really need that anymore, right? Because we've got nothing connected. So in some sense, we can actually build a much simpler processor if we went down this particular path. This is actually a very composable platform. So really what we're doing is we can build a single platform where now cards, we can have a Xeon card, an EPIC card, an ARM card, all plugged into the same server. This is just not possible today. The way we build our servers, we build a motherboard that is a Xeon, Sapphire Rapids motherboard, and all you can plug in are Sapphire Rapids or anything that's compatible with Sapphire Rapids socket. But if I need to go and build a next generation AMD EPIC system, I can't use that Sapphire Rapids board, right? And so I got to go build a whole another board to do that. Instead, what we're saying is you go and build a small little board that has the particular processor. It has whatever needs to be local. In this particular case, these green bars are DRAM. DRAM needs to be local, and then these boards get plugged into the chassis that is centered through Terminus. Things like HP Moonshot have done things like this before, but not really in the design of trying to be generic. They being super generic, but people have done this before. They haven't done the virtualization, the VIS capabilities much though that we know of. So really, now what you're doing is you're offloading your CSP code from the host server to the SmartNIC. So all of that code that was the hypervisor code, all of that stuff that was used to provide these services to the tenant get moved into this Terminus node. The tenant communicates directly to SmartNIC as we did, in the Azure offload that I showed in the last couple of slides. It communicates directly with SmartNIC, and so there's no virtualization software. It's just I talk to a network interface and I talk to a storage interface that's presented here. The SmartNIC then triages, processes, and transforms and steers all of the traffic that goes out. So really what it's doing is it's providing that virtualization capability. So the Xeon may, tenant running on the Xeon may be thinking that it has direct access to an FPGA or to a GPU or to SSDs, but in reality, it doesn't. And we can virtualize that. We can, do things like thin provisioning. The tenant may think it's got a terabyte of SSD, but in reality, it's only got a gigabyte. And we go, when it accesses the next gigabyte, we allocate on demand and so on. So having this virtualization gives me a tremendous amount of ability to make things look bigger than they are, smaller than they are, control, for security and for oversubscription purposes, and even control whether something's local or not. I might, I can now go and do things like paging, where I might, rather than having everything in local SSD, I could potentially page out to a remote SSD as well. Right. So this effectively is providing all of the virtualization capability, the security, and the quality service capabilities at this boundary here. So really, this is the Terminus boundary that we're seeing is the connection of each one of these devices into the Terminus nodes. you're really moving that VISC and control from cores into that SmartNIC. And so this is, by the way, useful beyond infrastructure. You can imagine doing computation as you're moving through this on your way to and from your endpoint, your final destination. And as I said, it simplifies the platform. Really, there's a huge advantage to being able to plug things in that maintain an I/O standard. So as you all know, PCI Gen 3 lasted for a long time through multiple processor generations. We needed to go and keep on building new motherboards, but if we did it this way, we would just build a small board. We maintain the PCI Gen 3 into a Terminus node, and we could actually have different generations of processors all plugging into the same overall chassis, right? So turns out from a system platform perspective, there's significant advantages to doing this. Okay, so if we go and scorecard ourselves, we give ourselves grades on how we're able to achieve the requirements using these three requirements. Can we do bare metal? You can, but you can only do it on a processor granularity. You can't subdivide a processor, right? Because remember, again, software running at whatever privilege level is going to be able to change anything. So it can change, the PCIe mappings, the second level page table mappings, and so on. So if you want to basically prevent one tenant from being affected by another, at best you can give bare metal offering on a socket basis, right? So cores can only see what the SmartNIC shows it. That's good, and QoS is enforced by the SmartNIC. Can we do arbitrary configuration of components? Can we go and build that 1,000 GPU system? Yes, we can with appropriate software, because we've got that SmartNIC is connected to the network, and so we could potentially do that. Can we do offload? We can almost do full offload. We can significantly reduce the cloud service provider code running on the host, means more rentable cores, but some code must still exist on the host, basically accessing specific control registers. Cannot be done from the outside. All right, so any questions here? Comments? Okay. All right, so the second step, the next step in this, is potentially going and looking at a processor and looking inside the processor. Can we go and push Terminus capabilities into the processor itself or into any particular device? So I'm sure that most of you know this architecture. This is an AMD EPYC, but what AMD EPYC processors are, the way they're constructed is they have core chiplets, some number of core chiplets that are then attached to a I/O die. So imagine if I go and attached to the I/O die is DRAM, PCIe, and so on. Normally, Ethernet is not necessarily attached directly to the I/O die. There's probably a NIC, but fundamentally, if we go and incorporate NIC functionality, we can have Ethernet attached directly to the I/O die. But if we take a look at this structure, what if we go and move that Terminus capability from this discrete component that we plug into a chassis, and we actually go and embed that functionality into the I/O die itself? Right. If we do that now, what we can do is we can go and embed our our VISC capabilities here, which gives us a lot more control at finer granularity than we could do in this kind of discrete version. So you're now changing the system configuration to a subset of cores, right? So basically what we can say is look, only this core chiplet is allowed to go and configure the I/O die, or you can move the cores that control the I/O die into the I/O die itself. You can go and throw some cores there, or you can provide external control to that. But now what happens is, basically none of the cores running tenant code has any control at all over the I/O die, right? So this gives us a tremendous amount of isolation compared to where we are before. I mean, we were only allowed to, within a whole processor, the tenant had full control. In this particular case, now we can isolate down to a single core chiplet, right? We can go and improve QoS now. So basically all access to DRAM goes through this I/O die. We can go and have QoS be controlled here, and we can go and provide appropriate crypto capabilities and so on to improve security. Now, one interesting thing here is this I/O die itself, can be used to go and build this discrete Terminus. Well, how will we do that? Well, we would take an I/O die and maybe keep one core chiplet to provide control, but then vacate all the others. But now what we do is we go and attach processors to the PCI lanes, right, that are available. So something like this is possible. This would allow us to also basically incorporate this DRAM that was attached to the SmartNIC and now gets folded into this device itself, because these DRAMs become part of that shared DRAM, right, across all of these everything else that we plug in. Okay, so what we're saying here is that, you know, even though maybe we can convince one vendor to build this, it's possible that we can use that same product to go and build Terminus nodes for other vendors' processors and accelerators and so on. Okay, so let's take a look at the scorecard here. Can we do bare metal? And now all of a sudden we can do bare metal on a core chiplet granularity, which is better than where we were before. Virtualization cost is enforced by the IO die, right? And obviously interconnect and security is also potentially provided by the IO die. Can we do arbitrary configuration components? Yes, again with software. And now at this point, no CSP code needs to run on the 10 and core chiplets. Because what we're doing is all the control has been now isolated. Obviously, if we need to be able to read a CSP, a particular control register on a particular core chiplet, we can ask the tenant to do that for us, but we don't need to, right? Fundamentally, we just say, look, we're just not going to go and touch that because that's really now the tenant's domain. The cloud service provider doesn't need to worry about that anymore. All right. So what if we go and do one step further? We go and take a look at this processor, and rather than going and leaving the core chiplets unchanged, let's go and say we're allowed to modify those as well, right? So right now, today, as we know, as we talked about before, there are second level page tables that are basically used by the hypervisor to provide the guest physical address, which is actually translated one more time. So the hypervisor can actually go and remap what the guest thinks is the tenant thinks is a physical address into a host physical address, right? So imagine if we go and take those second level page tables and enable outside control to be able to configure those and not let any of the cores running on the chiplet to be able to affect those, right? So if you do something like that, now all of a sudden you've now taken control of that particular component, these second level page tables, and handed it solely to the cloud service provider, which is exactly where we want to be, right? We want to have the cloud service provider doing this kind of manipulation, not the tenant themselves, right? Especially if you're in a cloud. You might also go and add additional quality of service capabilities into the interconnect, which would enable things like time division multiplexing or work conserving scheduling, which would then basically allow us to have a more predictable, jitter-free experience for a tenant. You may want to, cache partitioning is actually pretty pervasive today, but you may want to go and say the cloud service provider has control over that. So whatever it is, what I'm saying really here is there a way to provide external control over this? It may be that what you do is you just bind a single core, some small number of cores to that have that control, so you don't have to do this as making any significant silicon modification. Or what you do is you go and add control from the outside that enables someone to do this from the outside. Because what would be ideal is the cloud service provider doesn't need to have any code running here. They can go and issue commands from the outside to configure things and get things to operate in the right way. Okay, so this now enables full offload, the Viscas and core dies under CSP control, right? And this now allows me to go and give you a single core as a bare metal offering, right? Which is very unique. This would be something that is not possible today. Okay, so now we can go and do bare metal on a subcomponent level. Can have arbitrary configuration code as a no CSP code. So this is really fundamentally, all the way to the end and gives us all the capabilities we were looking for. All right, so long term though, where do we want to go in the really long term? Well, VISC under CSP control can be integrated into all components. So rather than going and saying, look, I'm going to have the centralized terminus, where everything plugs into, or do an IO die based terminus, or even do whatever. If I'm doing these all discretely, I can go and combine them. So what I can do is I can say, look, these terminus capabilities, these VISC capabilities are embedded in each one of my components. In this particular case, whether it's in the IO die or whether it's in the core chiplets or however it's implemented, we're actually pushing the VISC capabilities into each one of these components. Whether it's an Intel Xeon, AMD EPYC, ARM, Ampere ARM, SSDs, whatever. We can go and push these things in. You could imagine that there's some components for whatever reason, maybe they're too old or they decided not to do it. They don't have that, they didn't go and incorporate it directly into their silicon. So instead, what we can do is we can go and push that, we can still leave that in our smart network, right? So this is a not so smart switch, but potentially we have some this capability still left in there for these kinds of reasons, right? So this does not need to be implemented all in the same place. We can move these things around. In fact, you can offload this capabilities in some cases, like certain virtualization capabilities can be offloaded by sending the virtualization to another node, right? Imagine if the Xeon would send some of its virtualization traffic to the FPGA, which would then do it and then go and continue forwarding to wherever that particular request was going to go to, right? So this is something we're actually doing at Microsoft today in a project called Sirius, but fundamentally there's a bunch of different ways to implement this. All right, so path to disaggregated VM. So we've been talking about disaggregated VMs, throughout this talk, all the way from the first slide, our first motivation. What you really want to do is, the distributed VISC under CSP control really provides the underlying framework to assemble VMs from data center components, right? So being able to go and virtualize things at endpoints or in the network or wherever, as long as it's consistent and coherent, now allows us to potentially cut up our components in a way that allows us to give the tenants exactly what they need when they want it. So, for example, if I go and put the VISC capabilities, I can take, my FPGA and splice it in half, or take, my SSD and take a 1.5 of them, right? Essentially, I'm doing virtualization, which allows me to address, what allows the tenant to address that 1.5 SSDs, make it look like a single SSD, and then the interconnect and so on will provide the capability to then go and get the appropriate data from the appropriate place, or write the appropriate data to the appropriate place, right? Now, this is not easy at all. This is actually an incredibly hard problem to do. Actually, none of this stuff is easy, but this, just looking at some of the problems that we need to solve for disaggregated VMs, we need end-to-end control of this capabilities, right? Because we need to be consistent. Whatever this capabilities we provide in the processor core needs to be consistent with what the FPGA sees versus the SSDs and the GPUs and so on. So how do you make this consistent? How do you make this completely coherent? You don't want things to have different ideas of what the virtualization needs to be. So, and obviously then the VISC capabilities need to be compatible in some way. Virtualization is likely to occur at endpoints, but perhaps not through the entire path, right? So you can tunnel to an endpoint if you need additional virtualization, as I said, but it's quite possible that you need to do multiple translations. For example, I might go and, actually going back to some Ph.D. work that was done in my group, me and a few others, we were looking at a global physical address or a global virtual address, where the first translation may actually tell you what node you're going to go to, and then the second translation tells you exactly how to get to the data on that particular node, right? This gives you the ability to move things around in that node without having to go back and tell everyone that you're doing that, right? So you can see there's the potential for multiple layers of virtualization, right? QoS needs to be implemented across the entire communication path, right? You can't do QoS just in one point and expect it's going to, everything will be fine all the way through. Now, there are ways around this. You can basically say, look, I'm going to undersubscribe my network and have a lot of excess bandwidth. And so you can approximate, because it'll approximate a perfect network that way. But fundamentally, you have to have some strategy by which end to end you're able to go and make sure that QoS is supported all the way through. There's going to be interesting problems around, communicating across disparate networks. I might be going across, PCIe initially, which, has certain potential. You need to potentially add some QoS. Then go through, a standard Ethernet network. You may go across PCI again. You may bridge to another network, maybe an InfiniBand network, a WAN, which is still going to be Ethernet, but potentially with very different characteristics and so on. You need to be able to deal with all of these disparate networks as well. And, there's also a tremendous number of reliability, telemetry, and serviceability issues. How do you ensure that this is reliable? If I'm starting now, what I'm doing is I'm spreading my VM from, instead of being on one server, It's now spread across N servers. And each one of those N servers could go down. There's a probability that each one of these N servers is going to go down. So the overall reliability of your VM, when you go from one server to N servers, is going to reduce if you don't do something about it. How do you deal with all of the reliability issues that come up? How do you go and address those in a way that's coherent and consistent with everything else, the VIS capabilities that you're implementing? Even telemetry is an issue, right? How do I then go and figure out what's going on in my system? How do I go and export the appropriate telemetry saying, oh, this is the kind of activity that's going on. Here's how to debug bottlenecks. Here's how to debug faults and so on, right? So the telemetry is going to be critically important. And how do you do serviceability? Serviceability is how do I go and update for bugs or to add new capability? So you can imagine if I'm running on a single server, I can update that somewhat consistently because I'm just going to update everything in the server all at once. But imagine now I've got to potentially update different things at different times. How do I coordinate? How do I deal with traffic that came before the update occurred, assuming the previous version of the software is there, and so on, right? There's a tremendous number of problems and that need to be solved to get this to work. But I think these are great topics for us to all work on as researchers. All right, so in terms of discussions and conclusions, the Terminus, at a high level provides this VIS framework needed for future data centers. I mean, we actually Terminus, VIS capabilities are there today. But what I would argue is in many areas they're incomplete, and in many areas they're not consistent. And so I think if we think about this overall as, we need to go and implement these capabilities, look at how we might want to build data centers in public cloud in the future, and be able to come up with a coherent story, I think that we would all be better for that. The current processor design does not support, Terminus in its full glory. I mean, it clearly has some virtualization capabilities, some security capabilities, some quality service capabilities, and some interconnect capabilities, but it does not support the full vision. And especially if we want to get down to something sub-processor in terms of bare metal kinds of capabilities and full offload, right? Logically moving Terminus out of processors makes processors themselves a composable component. It provides much more flexibility, scalability, and efficiency. Processors then could focus on cores and DRAM, right? They don't have to deal with all of this extra uncore, which fundamentally could live somewhere else. In reality, if you think about processors and how they were designed and how they were built, when I was a grad student and as an undergrad, I used to go and buy processors distinct of the chipsets, right? I go and buy a chipset made oftentimes by a different manufacturer than the processor. And that chipset would provide essentially the memory interface, as the north bridge, and the I/O interface, which was the south bridge. Really what we're saying here is, what if we went and took the processors apart again and kind of had the north bridge, south bridge, or at least the south bridge live in the Terminus device? That would allow us to have complete control over the virtualization, right? And obviously it doesn't have to be a truly discrete device. What it can be is a virtually discrete device by enabling the cloud service provider to control things from the outside without having, not letting a high privilege level software running on the processor itself to be able to control that south bridge functionality. So all components are now potentially equal. This is democratizing our data centers rather than processor cores being the kings and everyone else is the serf that serves the king. Now processor is yet another component that can work together to solve the problem, right? So this is a really it does offer a lot more flexibility, a lot more capability than we have today. This also enables fine-grained bare metal. We think that, or at least I think this is a very, very valuable thing to do. It gives us a lot more isolation. I think it's a much better offering that, for our tenants to be able to say, look, there's going to be no jitter introduced by anything, right? Except for yourself. And this is, you can get better usage and more composability, right? So one of the things that needs to happen to make this vision occur is we really need to democratize APIs. Right, most APIs, or many of the APIs that I see today, are actually very processor focused still. For instance, two of them, DSA is a data streaming accelerator from Intel, and CXL is the open standard. DSA, when Intel folks first, showed this to me, I thought this was great. What it does, part of it is it allows you to NQ and DQ commands, to get something to offload work. And I said, fantastic. I want to be able to do NQ from my FPGA to a processor core. And turns out that that's not supported. Only the processor core is allowed to enqueue to peripherals, not or to other cores, but peripherals can enqueue to processor cores. So to me, this is not a democratized API. It is core-centric. We need to fix that. CXL also, I was asking for, very excited about CXL. I was asking for the ability to shoot down TLB entries from peripheral, and turns out that's not supported. So these are things where I think we need to improve our APIs to make them less core-centric and make them more democratized. But these must be industry standards. These are things where we can't, Microsoft can't do this unilaterally. This has to be something that the industry takes on as a goal. So to me, this whole area is very rich for research. What are the best ways to partition? Some of the questions are I list here. How should this be implemented? Where should they be implemented? When should they be implemented? What are the APIs and how do we get there? And how do we standardize? Right. So it's a bunch of things that we can do here.